Good afternoon, everyone. My name is Wijnand Marquart. I'm a PhD student at the University of Cape Town in South Africa. And today I'll present to you some work that we've done on the use of iron nickel nanoparticles on metal oxide overlayers supported on alumina. And we use this for the CO2 oxidative dehydrogenation of ethane. So we're all aware about the fact that we need to reduce our CO2 emissions and not only reduce them but also utilize them. And currently commercialized processes utilize about 200 metric tons a year. And this is by far not enough if we compare it to the CO2 emitted in the world by fuel combustion alone. So catalytic processes that utilize CO2 at the moment are CO2 hydrogenation to produce fuels, as well as the ethane dry forming to produce synthesis gas. So in this study we're looking at the CO2-assisted oxidative dehydrogenation of ethane, and that produces CO, ethylene, and water. And ethylene is one of the largest chemical building blocks at the moment, and currently it's produced by mainly by steam cracking, which uses water fuels as the feedstock, as well as it emits a large amount of CO2. So other possible processes synthesizing ethylene are currently not economically viable because they are compared to the current capabilities of the steam cracking process. So as our previous speaker already indicated, that the use of metal oxide catalysts is one of the more common catalysts for this process, and they go through a Marsman flavor type of mechanism where the ethane reacts with the surface of the metal oxide, reducing the surface, creating an oxygen valence state vacancy, and then producing water and ethylene. And this is followed by the reoxidation by means of CO2 activation and producing CO. So in the study by Cargo et al., they have evaluated a wide range of metal oxides for this reaction, and they have found that a large variety in performances within the various metal oxide materials. So we are looking at creating a bifunctional catalyst that can activate the ethane as is done by a Marsman mechanism, but as well we're loading this metal oxide overlayer with iron nickel nanoparticles with 3 different ratios, 1:1, 3, and 5. And what we're looking at is that the monolayer activates the ethane, producing ethylene and water, and that the CO2 is activated on the iron nickel nanoparticle, making oxygen species available to reoxidize the metal oxide. So these metal oxide monolayers or overlayers are created or synthesized by the incipient wetness impregnation technique, and this is to create a support material that has the chemical and electronic properties of the metal oxide, but it remains, it preserves the structural properties of the alumina support. So by means of UV spectra, we have been able to measure the acidity of the various oxide supported samples, and we observed that when we load vanadium and chromium oxide, we can increase the acidity, and when we load, for example, samarium oxide, we decrease the acidity of the alumina support significantly. So iron nickel nanoparticles are created by a surfactant-free hydrogen decomposition route, and this to synthesize nanoparticles that have close intimacy between the two metals of nickel and iron, which is compared to the incipient impregnation technique. So these 3 different ratios of metal oxide, iron to nickel ratios, created a spindle structure, and at the 1:1 ratio we also observed some nickel hydroxide, which is due to the stoichiometric amount of nickel in the sample. So to reduce these iron nickel spindle structures, we expose them to reduction treatment, and we follow the developments of in situ HZ, and we can observe the formation of the alloy at about 300 degrees Celsius, and we also observed different crystal structure composition between the 1:1 higher iron content. So the more iron in the structure, the more BCC phase we have in the final composition. So, as we proposed that the iron nickel nanoparticles creates the CO2 activation on the sample to enhance the catalytic activity of the entire system, we performed some CO2 activation experiments and also followed this by means of in situ XSP. And what we can observe is that the CO is formed at about 300 degrees Celsius, and this is goes with the simultaneous reoxidation of the alloy into the spindle structure. However, the BCC phase is the only phase that seems to be oxidizing, and the FCC phase remains resistant to the oxidation in the current conditions. When we increase the iron content, we saw we have a higher BCC content in our final alloy composition, and this also means that we have a much higher CO formation rate, as well as a higher reoxidation during the CO2 activation experiment. Again, the FCC phase remained unaffected. So now on the monolayers, we performed CO2 oxidative CO2 reactions on all of the monolayers. So this is without the iron particles, and we exposed them to a temperature of 600 degrees Celsius at a 1:1 feed ratio of CO2 and ethane at 1 atmospheric pressure. So we exposed these samples to 24 hours downstream, and what we can observe is that from the 6 monolayers, zirconia, chromium, vanadium, gallium, titanium, and samarium, we observe that the unreducible and low acidity monolayers show varying activity. However, the reducible zirconia, the reducible vanadium and chromium oxide samples, and as well as the slightly more acidic gallium oxide sample, have some dehydrogenation activity, but we can also observe that we have very limited CO2 activation. If we look at the selectivity, we see that we produce quite a significant amount of ethylene, but I would like to explain the selectivity because it's calculated based on carbon percentage. And if we look at only CO2 APH behavior, we would have 67% ethylene selectivity. If we would have increased selectivity, then the direct dehydrogenation reaction is becoming more dominant, and if we produce a lot of CO, we would have most likely the dry forming reaction happening. So the spent samples of these catalysts, they contain a lot of carbon on the surface, but what we did also observe in situ in the offline XCD patterns is that the monolayers did not sinter, and they remained as a monolayers system. As you can see, that all the oxide monolayers contain mainly alumina and support the pattern. So, now we know that the iron nickel nanoparticles onto the zirconia monolayer, and we do not observe any change in activity compared if we look at the ethane conversion. However, we do observe a slight or significant increase depending on the iron nickel ratio of CO2 activation, but that dies out pretty quickly with downstream. What we do observe as well is the difference in product selectivity. So the 1-to-1 ratio of iron nickel predominantly performs the drive from the root, and if we increase the iron content in the nanoparticles, we increase also the ethane production. So the spent samples showed significant oxidation towards the spinel structure. However, again, we only observed the oxidation of the BCC phase, and the FCC phase remained unaffected. This is shown by the 3 different ratios, where the higher iron has a higher BCC phase, so it also has a higher oxidation, reoxidation. So now we learned that also chromium oxide, the 3 different ratios, and we can observe that 5-to-1 ratio did not enhance the activity of the catalyst significantly, but once we loaded the 3-to-1 and the 1-to-1 ratio, we had a significant increase in conversion levels for both ethane as well as CO2. But this is paired with a full-on dry forming at a 1-to-1 ratio, and we only observe a slight amount of dehydrogenation in the 3-to-1 ratio. Again, the spent samples are oxidized towards the spinel, but again, only the BCC phase. So now we looked at the Raman spectra as well in the spent samples, and we observed again a lot of carbon composition happening, and we tried to quantify this amount of carbon within the different samples, and we looked at the TGA and burnt of the carbon to calculate the amount of carbon we can remove. So the inactive zirconia sample shows a slight drop in weight compared to the more active chromium oxide alumina sample. So here we find a significant drop in the weight at about 400 degrees Celsius, which is the carbon removing from the surface. So upon lowering the iron in the particles, we observe that we have a decrease in carbon deposition under reaction conditions, and with a decrease in the iron content, we also have a further decrease in the carbon deposition. Interestingly, the 1-to-1 phase showed a significantly higher temperature required to remove the carbon, and this would indicate that we have a more prolific type of carbon, which is also shown by the Raman spectra, where we have a swap between the D and G ratio. So finally, we loaded the 3-to-1 nickel iron to nickel nano as one of the various monolayers present, and then what we can observe is that, so these are the monolayers, their monolayers, and then upon loading it on chromium, just to remind you, we have a significant dry forming activity happening, but then when we load it on vanadium oxide, we have a significant increase in activity as well, and but again, a significant amount of dry forming. We do observe a slight increase in the direct dehydrogenation reaction with downstream. Then the gallium sample, it did not necessarily make a massive improvement in terms of activity, but it did improve its stability, as well as the selectivity was closer to the ODH reaction ring missing. Titania improved significantly in terms of temperature, in terms of composition compared to the big monolayer, and performs relatively similar to the gallium oxide sample. And then the samarium sample did not improve in terms of composition compared to the big monolayer. So, just to conclude this talk, we managed to synthesize overlayers that have the chemical and electronic properties of the metal oxide support, but it gets the structural properties of the aluminum carrier. We also observed that these monolayers do not activate CO2 significantly enough, and that the activity is very dependent on the acidity and the reducibility properties. But once we loaded the ionic alloys, we observed that we can actually increase the CO2 utilization, but this is very dependent on the type of monolayer and composition of the catalyst, or the ionic particles. So we created a tandem reaction between the monolayer and the ionic particles, but like I said earlier, it is very dependent on the acidity and reducibility properties of the own layer, as well as on the ionic composition. And this means that the optimum ionic composition is very dependent on the metal oxide overlayer. So I would like to thank you for your attention and the following institutions for their funding, and specifically these people for their contribution in the work. And Shane is the PhD student of this work. He unfortunately wasn't able to present himself, so I'll try my best to answer your questions.
Okay, we have time for one question.
I was wondering about the WH distribution of the space velocity in volume, or what was the weight of space velocity? So what was the weight out space velocity?
Yes. So it's about 25 miles per minute, 100 milligram catalyst, so it's 50 meters per hour.
Okay, so next time I'll speak it again.
Okay.